Welcome back, everyone. We are incredibly excited today to have a special guest, Dr. Mrinal Iyer, on the show with us today. Mrinal got his undergrad at IIT Madras, where he decided that he wanted to make some ships. And at sometimes he decided that ships weren't nearly as interesting as chips. So he decided to move from the world of ships to chips, and then did his PhD at the University of Michigan, where I think he completely shifted from engineering water-based devices to solid-state devices, which I think was super fun and interesting that he went through that transition. After an illustrious PhD dissertation, about 99% of which I probably will not understand, he moved to Intel in the Pacific Northwest, where he continued his journey with semiconductors and all the cool stuff that Intel makes. And he's since been involved with a bunch of very interesting companies in the area, GraphCore, which is one of the leading edge AI specialized chip makers, and then Modular, which is similar to GraphCore as well. Outside of all these incredible professional accomplishments, Mrinal is also an incredible athlete. And the fun story here is that in his first year at IITM, he had a roommate who, and he was roughly the same physical size as that roommate, but then that I think geometry started to diverge quite significantly every year since then. And one of them weighs more than 200 pounds today, and the other has competed in multiple Ironman triathlons. I only wish one day maybe we'll get to meet them.
Roommate very well.
Yeah, I think we'll get to meet him someday, or maybe we already have. Who knows, right? It's one of those things, mysteries that we'll never be able to solve.
Yeah, I'm really surprised you know the weight as well, right?
Yeah, it's one of those rare friends with whom we actually meet up. We talk about these like very specific topics.
Yeah.
It's a very good friend. We go such a long way. Yeah, quite a long way. Probably like as old as I am, probably.
Exactly as you are.
Welcome, Mrinal. Very happy to have you.
Thanks for the fun introduction. Spoiler: Siddharth and I were the roommates. And,
oh man!
and since the singularity, we've gone in different paths. And but yeah, thanks for the great intro. To just add a little to what Siddharth just mentioned, I have spent at least last 7 years of my career in various chip companies, all geared towards making ASICs for AI. So these are AI hardware accelerator companies. And the joke that I always have is I've spent my career trying to beat NVIDIA, and it's taken me through 3 companies and 4 architectures, and the fight is still on. And right. So you can see that the rest of the talk is coming to why NVIDIA is such a big king in this field. Goes back to like why do they have such an entrenched position? We will probably cover that today.
Yeah, we'll start from the basics, Mrinal. So starting with some of the words that you mentioned, right? So what's an ASIC, right?
Thank you.
What's an architecture? So let's go through that, right? So what's an ASIC? And yeah, in your own words.
So when most people think about a chip, the chip that goes into your, what we're most like comfortable using are those in our laptops or in our phones. And these have been called as central processing units, or these are good general purpose programmable devices. ASICs are application specific circuits. So what they allow you is, if you have a given budget of transistors, let's say I have 50 billion transistors that I can play with. If I design all of them with the sole purpose of doing one or a few set of applications, you get something called an ASIC. ASICs are closer than they're not as far as from what we are used to. The phones that we have already have ASICs in them. For example, the modem that's required, the Wi-Fi chip. These are all like tiny ASICs which are geared to just doing one thing correctly. The LTE modem from Qualcomm in most people's phones just handles cell phone signals. The Wi-Fi chip, which typically comes from Broadcom, specializes in basically taking Wi-Fi and converting the data in and out from between devices. So ASICs are part and parcel of our daily life. Now, same thing is what's happening in AI. We're getting these as the workloads are maturing towards a particular into a particular family of possible models, the chips are getting more and more specialized. And why do we do all of this? Is to just get it either lower in power or faster in speed. That is the only two things that we are always trading off.
So just to dig deeper there, so ASICs are essentially application-specific integrated circuits, right? So essentially application-specific chips. So just to give a sense of how many ASICs are there in a phone, right? So how many ASICs are there in a phone, MacBook, for example, and so on? So what's the order of things?
My guess is there's one for there's one for Wi-Fi, there's one for LTE, there's one for there's a tiny graphics card inside it. There is an image, decoder. So all in all, at least 4, and probably if you're Apple, you have many more, motion units and so on. For every particular sensor, they also sometimes have a specific chip that just deals with the whole, just processing data from that sensor very easily.
Right.
As an example, we have Face ID. Initially, it makes sense to run it on your on the standard Apple chip, but then if it's very commonly used, you don't want your Face ID to drain out all your battery anyway. So it's good to then just shift that algorithm into a specific chip, and run it at much lower power so that it can be ambient.
So Mrinal, if I understand what you're saying, it's a bit like instead of having a brain in your head, you're kind of pushing the brain closer to all the different sensory areas. So it's almost like having a mini brain in my tongue
and
that just knows how to taste stuff and nothing else. And it's a very highly simplified brain. And a similar brain in my eyes that just knows how to recognize pictures of Marilyn Monroe, who's one of my favorite actresses, and things like that, right? So it's and then there's maybe a little part of the brain in my fingertips to help me identify when I'm touching. This is getting really, really shady, but maybe a piece of cloth that I really like, or some texture that I really like touching, maybe a cat or something, without it seeming too awkward. Yeah, that kind of, is that what you mean by
that's exactly. And what your so the technical word for it is called SoC, which means a system on a chip, and you have basically a central chip, which is your brain or the CPU, which controls all these peripheral chips. And then, is always trading information, sending one to the other, and then deciding what to do with what comes from these peripheral chips.
So that's why, I guess coming back to now, these application-specific chips. Now, the applications could be as simple as touching a cloth, right? Or opening a door, right? Or detecting some visual feed. Or in the case of, let's say, washing machines or things that are used in cars. So they can be very simple chips as well, right? Is that right, Mrinal?
Yeah. The biggest seller is they should be really specific. You can't have too many things, and as long as you can specialize and say that this is the math that I care about, and all the math that I do is just going to fit into these 2 or 3 buckets, then I can design a chip which just takes bakes the math down into the silicon, and that allows you to save a lot of power.
Yes.
Well, a calculator that can just do addition, and a different calculator that just does multiplication, and a different one that just does subtraction, is what you're talking about. You'd use 3 different.
Yeah, I mean, yes, if you want to say it that way. But these are all they're all calculators which can do all sorts of calculations. But they're wired, and some of them are specialized for doing trigonometry. Let's say some of them are specialized for doing, some other, square roots, and exponential signal processing. So those kind of things. But they all do adds and subtracts.
Right.
Okay. It was too basic. Maybe not that basic. Maybe not that specialized is what you're saying.
So before we deep dive into AI chips itself, now we are living in a world where AI is going to play a major role and people are fighting for that. But before that, I would like to understand what's happening in the world, right? So I hear about these chip shortages, and is it all kinds of chips? I hear about them in cars and washing machines. But what's the story? What's happening there?
So that's interesting. So steadily, more and more devices are getting more and more, ability to be remote controlled or run, logic automatically. It's more and more logic coming into them. So washing machines, for example, you can start them remotely. Dishwashers can be, heaters can be made to turn on and off at whatever time. Same with lights. So to be able to control them remotely, you need like a chip inside it. These are not very complicated chips. These are, the simplest kind. These are called microcontrollers. All they do is like you have 10 options. You can either take a light, you can turn it off, turn it on. You have a clock inside it, which tells it at this time, turn it off or turn it on, and those kind of things. So these are very simple. They allow you to do a few set of things. And these are called microcontrollers. These are very common in appliances today. Few levels up are cars. Cars are like much more complex chips because they sometimes control how much petrol can actually go into your engine. So even if you floor the gas, they actually measure what's the rate, what's the temperature, the ambient temperature inside the engine gasket, and then control the ignition based on that. So allowing you to get much more mileage. And then they control several other things. You have your car has your app display. It allows you to tell you to set your time and play a bunch of music and all of these. So, but the logic here is not very difficult. These do not compare in complexity to what goes into your phone or your laptop today. So the challenge which has been happening when you hear chip shortages, it's actually limited either to the lower end devices like your appliances or to extremely popular higher end devices. So if you're someone for multiple reasons, like if you're a Ford, they always operated on just-in-time JIT manufacturing. So they do not build up huge inventories. So they depend on, everything just coming in place and for efficiency reasons. When it happened that everybody wants more and more devices, it so happened that the factories got full and they always started prioritizing devices which get them more money. Chip from Ford will probably, Ford will buy it for, $20 to $50 or, in that ballpark. But if you have an NVIDIA coming and buying a high performance graphics card manufactured from a factory, this is going to cost anywhere from, a few hundreds to up to $10,000. So there is much higher margin to be made there. So what you started seeing is factories basically started prioritizing what's going to make them more money, and because they were running 100% of the time anyway, and so that resulted in a huge problem for everybody else, the lower end manufacturers, compounded by the problem that they are just in time. So they did not have any inventory to last them more than a few months of production.
Right. So it looks like it's more of an inventory management and operations problem. That's my area of research.
That's true. And today, if the same thing were to happen, the car chips are not going to get, the appliances are not going to get any more expensive. The chips will continue to cost the same, a few dollars to a few tens of dollars. The right solution there would just be build up huge inventories and then scratch it or build it in a way that you can keep upgrading the software on it, but invest more into chips. And that basically would be a simple way to fix it.
And what's the economics here? So why can't we just, let's say, airlift unit in Taiwan, right? And put it up in Texas. So what's stopping here? So is it the cost of land? There's a lot of land in Texas. So what's the issue here?
Actually, on that note, are they only manufactured in Taiwan? Where are these things coming from? Even that I don't know. Is it Taiwan or is it China or I thought the US? It doesn't Intel manufacture tons of chips in the US?
That's a good question. So in the US, there are only two companies which manufacture logic chips, like the ones we talk about in the phones and laptops and the advanced chips. They are global foundries, which used to be owned by AMD. And then there is Intel's own factory, which makes only Intel chips, and which are pretty much only what goes into your laptop or in a server. There are a few others, but these are not as competitive. The major competition to the American manufacturers is from the Taiwanese, and the spearhead of this is TSMC, which is Taiwanese Semiconductor Manufacturing Corporation. It's the most valuable company of Taiwan and probably among the most valuable in the world. They are the most the most advanced, and then there is Samsung in Korea. So these are the major high-end manufacturers. There are other lower-end manufacturers in China. China also has a huge role in labor-intensive parts of assembling chips, sorting them into your medium quality, top quality, because you can, if you have, in your laptops, if you have Intel chips, even now you have i3s, i5s, i7s. These are all manufactured together. It's just that i3 has some defects. It's still good enough to run, so they discount it and sell you, market it as an i3 chip, which is, it's not a different chip. It's just a chip with some flaws in it. But these flaws are not enough to make it stop. They're just, they are simply, they're functional, but they're not as fast, not as efficient as the i7s. And you pay much more for i7s. But they're all from the same wafer.
You're saying it's the same chip that's just sold at a cheaper price because there's a possibility of a defect?
Oh no, there's the same wafer. So you have a wafer, and a wafer has several hundred chips in it, every square inside a big circle, and typically ends of the circle, it's harder to get good quality manufacturing at the end because of all sorts of optical problems in when you manufacture. It's a part of manufacturing. So you always right in the corner of the chip and right at the center, you will always have chips which are less quality than the ones in the central ring. So these are things which will, for example, be sold at higher prices than the ones in the corner and the centers.
So you're saying it's the exact opposite of a pizza or a dosa, where I think the tastiest parts are the edges and the center. You're saying it's the opposite with chips.
It's the absolute opposite. The center and the edges are the ones which are discarded the first, or sold cheap, or just absolutely junked. And then everything else is sold at higher prices. But coming to manufacturing, so these are the companies, and TSMC is the best of the lot. Samsung is very good at manufacturing memory, and that's a great visual. That's what a wafer looks like. And as you can see, each of the squares within the wafer is a chip. And what I'm saying is that the ones closer, in the central ring, are the better quality. The ones closer to the edges and the center are typically worse quality. And so we're back to so Chaitanya's question was, what is the challenge in taking a factory and replicating it?
Right.
In fact, when I used to work at the factory, there used to be an entire slogan called "Copy Exactly," and which actually speaks to how difficult it is to take a factory doing one set of processes and exactly copy it in another factory, even within the US. So, Intel had factories, let's say, in Oregon and Arizona, and taking one and taking it, and replicating the same factory in another state is really, really, really hard. You have all sorts of excursions, and many times the issues are way outside, this typical statistical zone of comfort. And Intel also then started pushing manufacturing to Ireland. And those factories were, had a long period of time, long is relative, but they had a period of time where they were just manufacturing, but they would not hit the same quality as the other factories. And it took them continuous, iteration, clever, debugging to figure out why exactly they were off, even though procedurally they are exact. You have the exactly same menu, same recipe to follow, but you will not get the same level of output out of it. So, and that is the same company, same set of people, same management chain trying to create two factories. Now compound the problem of different companies trying to move across the globe and set up plants in the US. The TSMC founder has come publicly many times to say it is they were not interested in coming to the US. So it is only after heavy subsidies, which basically gives them a huge run-up time where, they might be just producing junk for a while before they figure everything out and start producing top quality, that they will be able to produce from both locations, from US and Taiwan to equal quality. And it's expensive because you have a fully functional factory just producing garbage, and that is hemorrhaging money. And it's basically these subsidies which kind of cover that and soften the blow and make them just shift.
I mean, what you're saying, if I understand, is that what McDonald's or Subway or every other franchise restaurant has figured out, which is to like create the same thing in 100 places with the exact same quality, you're saying is hard to do in the world of semiconductors.
Very, very hard to do. That's a very good analogy. Scaling out has been really painful.
You just get like maybe like Intel's new studio should be like, yeah.
But the precision required is very high, right? So not like, hey, the burger, okay, if it's a centimeter here and there, it would not matter. But here it's like we are talking
it's a couple nanometers off, you're dead. And
so
tens of nanometers, it's over. Yeah.
And a nanometer is like what? 1 millionth of a meter or something?
10
or
to the minus 9, right? Is that right?
Which is
minus
a billionth,
9.
Right? So it's a billionth of a meter. Yeah. Which is, I don't know, a gazillionth of an inch in the way we describe things in the US. I don't even know what inches are. Or like
That's
feet.
Right. So yeah, but it's so a couple tens of nanometers and it goes.
A sense of the size, a COVID virus, which is really small, of course. It's 60 nanometers. So it's like, so COVID virus, it's 60 nanometers. So we should not be off by a single virus.
Yeah.
Wait. So this is the size of the transistor that's on the chip.
That's right.
Wow, that's the size of a COVID virus.
It's smaller. It's actually much smaller, but you can't tolerate errors more than half a COVID virus or up to a COVID virus.
Wow. Okay.
So that is how how crazy the accuracy requirements are, and that's what causes it's a really difficult problem to copy exactly.
But these are made by machines, not humans, right? I mean, it's not like a guy flipping burgers or something. Like there's like some very specialized equipment making these. Why can't you configure the equipment the exact same? Like what? That's what I'm struggling to understand.
So as an example, right? Like the way it's almost fully automated. There are very few humans actually involved in the process. You're just setting the overall recipe, but it's like you have a wafer, and the way you build up transistors is you hit it with a laser, and you have parts of the wafer which are masked out and parts which are not, and wherever the light goes through, those those become the transistors. You have little squares patterned where you want the transistors, but the challenge is what is the depth of once the light hits the wafer, there is a chemical which sits there which actually changes properties according to whether light hits it or not. And if light hits it, it becomes very soft, and that can be removed away easily. But this is mechanical, so it depends on the coating that is applied is about not in nanometers, it's in angstroms. It's a tenth of nanometers. So you can have errors there, and this is a very mechanical process which just spins. You drop a liquid, spin it, and then that just perfectly spreads around. But then you can have like variations, and you're talking about these kind of variations across a wafer which is 300 millimeters in diameter. So if I were to take an analogy, it's like talking about a pizza, but then you're talking about a tiny piece of a tiny piece of a flake of oregano. You take a flake of oregano and then take a tenth of it. A small error there is going to cause you a problem with the entire pizza. So that's your that's the challenge basically with even if it's fully automated to get it out correctly.
So just to show these size of these things, right? So you have the human head that looks like a mountain here, versus coming down to Zika virus. So that's the smallest one that you can see here, which is still in nanometers, right? So it's not even it's still micrometers. So
it's microns.
Wait, so what does 0.045 micrometers mean in nanometers? That's like 45?
45 nanometers, correct. That is
okay.
Right.
And the size of a transistor is what again? Around the same thing?
The latest transistors are somewhere there. Yeah.
Okay.
In that ballpark.
Yeah.
And you're saying that an error of the size of like this, like an error, if the laser just like burns a little too much or a little too little, to the tune of just a few nanometers here and there, would materially change the outcome of like whether the transistor is usable or not.
Alive or not. Yeah.
Wow.
Yeah.
So it's a very, very...
It's a mechanical process, which is the core problem, right? It's like it's not. I mean, we're used to just imagining the world with like just a bunch of digital stuff, copy paste, and all these things that we do on the internet all the time. Like this is where the digital world interacts with the physical, and like the limitation is now physical processes.
Absolutely, it's very, very sophisticated, and it's a very hard problem to get it correctly.
So this is the world's smallest transistor. It's about a nanometer. So literally going to the atomic level, not atomic, I guess molecular level, right? At this stage, I don't even know the difference. Yeah.
Wait, so Chaitanya, that's 1 nanometer, the entire transistor?
That's the smallest one. Yeah.
Wow.
This is far away from production. Let me tell you. This is proof of concept to say that it can be done, especially if you have carbon nanotubes. It's a completely different mechanism from what's done in practice. The challenge with manufacturing at scale is you have to make 55 billion of these, and many of them almost, they all have to be like correct.
Right.
And that's where, it's if we can get to a point where we can manufacture, about 100 billion of these like correctly, that'll be awesome. We'll see a huge jump in like the capabilities of computing way beyond what is available today.
And Wendy, we were talking about Moore's law just a little earlier, right? And we talked about how like that had doubled transistor capacity every 18 months or so.
Right.
You're saying that had reached a natural limit, and that was the problem. That's what I think we were talking about earlier.
Yes. So we cannot keep on increasing that, because now we have reached the limits of physical space, right? Literally going down to nanometers, and I guess this is where we could the semiconductor based, the classical computing probably will stop here.
And the reason, just to be clear, the reason why when you say limits of physics, like we're going down to the size of individual molecules and atoms, and that's why we can't go any further than that.
Right.
Gotcha.
And it's also the question of our current way of creating transistors. Transistors, after all, a gate. So it's like, if you want to think about this schematic here, if you squeeze the tube, nothing will go through. If you keep the tube open, like it's a things will flow from one end to the other. But transistors are logically just gates. You can either turn it on or turn it off. And the way we do it today, using the standard silicon base by doping silicon and so on, that is reaching its limits. Now, if these open up, if we can take the nanotube based methods into production, into large scale production, we're back into Moore's law again. That's a completely different paradigm. But with what we are doing today, which is just continuous refinement of the standard CMOS technology, we are massively hitting limits today.
Right. Cool. And just to push a bit more about what's the state of the art, right? So, for example, so I came across this chip by Cerebras. So they have 1.2 trillion transistors. And looks like the one that they're comparing against is with the NVIDIA one.
That's right.
Yeah. Could you tell us a bit more about?
Yeah. So, so Cerebras' chip is not a chip; it's a wafer. The entire wafer is treated as a single chip. So what's typically done is, imagine, so Cerebras, this is the wafer. Now, normally you would, like, all the little circles that you see, all of them, that's where you start cutting the chips and selling, like, all of these 800 different copies. But what Cerebras, took the bet is that if we are patterning this wafer, one wafer at a time, why don't we just, use the entire wafer towards just, gear it towards running this AI model? It comes with its pros and its cons. The pros are that, if you are having 5 different chips, you would need wires to connect them. And wires are where it gets really slow and where it consumes a lot of power, and that becomes the new bottleneck. But if they were all part of the same silicon, they're talking to each other as fast as they're talking inside each other. So your inter-chip communication is blisteringly fast. The challenge is the fact that not all of these chips work at the same time. You're manufacturing a wafer, and as we discussed, no wafer gives you a full yield. Some chips will not work, or will be of lower quality, will be all of this. You're all trying to handle everything. So every chip that Cerebras will sell will be of different qualities. They'll have some pieces, some fraction of the chip that doesn't work. And they have to manage their software so that they can avoid all the dead silicon and basically use the parts which are working. And it's a humongous challenge. The second major thing which they've solved, which was a massive engineering problem always, was transistors operate at 0.9 volts, and that's the operating voltage. Go any lower than that, the transistors fail. The entire logic starts failing. Go higher, again they can't take it. So it's a very tiny 0.9 volts that they operate on. Now multiply all of these transistors by that kind of voltage, you're having a huge power draw. I'm talking of the order of tens of thousands of amperes. That's what these chips need to be supplied with at a very low voltage, at a voltage of 0.9 volts. So it becomes a giant engineering challenge to make a wafer-size chip. But how do you keep this supplied? Like, imagine a chip which has to always ensure that every transistor gets 0.9 volts. So it's a giant engineering problem to get those kind of power supply units which can keep it sustained. They've solved that problem, but they have other problems of, they have a much more complicated software which just does not work in. It's not as easy as GPU, and GPU itself not easy. So Cerebras is like an order of magnitude harder software, and they have other giant challenges which we can get to about when it comes to just handling large models of the type which are coming in GPT today. But that is
So just to understand the state of the art, so it looks like Cerebras, which is about 1 trillion transistors, it's getting close to the number of neurons that a human brain has. A human brain has about 100 billion neurons. 86, taking the Nature article, 86 billion neurons. So literally, we can have a transistor representing every neuron, right? Or even transistors of every neuron. So we are reaching that. I don't want to call it singularity, but getting there, right?
Yeah.
God.
But of course, these transistors to neuron equivalency is a false equivalency, because it doesn't mean that the chips are getting smarter, better, or anything, or it's just a number to throw around. This could absolutely mean we might need like 100 trillion transistors before we can match the brain of a frog. So it's just not clear today.
So is it because a neuron does much more than what a transistor can do? So a transistor is mostly discrete signals. Neuron can actually capture signals. Yeah. Right.
And neuron has a state, it has plasticity in the neuron, so it is able to remember and all of that. And these don't exist today.
I mean, the other thing I was thinking of, like, the neurons are also like 3-dimensional, whereas why are we building all these things like flat? Why can't we build them in 3D? Like, that's always so bizarre, right? Why are we just spreading it onto this piece of paper? Like, we have 3D printing and all this shit that we talk about, pardon the French. Like, why can't we use like 3D, like whatever, chips instead of this planar design? That just seems bizarre.
That is a very deep question. And I'll give you two answers. One is that, what you see as 3D is not, it's actually, what you see as planar is not planar, it's actually 3D. So every chip has, like, imagine it's a skyscraper with 100 floors. That's the number of layers you basically required before you even build a chip. And why do you need these? Like, imagine just the transistors at layer floor 0, but then you need to connect them, which can be floor 1, and then you need to connect groups of them, which is like even bigger groups of them, and then you add that keeps going through more and more levels before you can start connecting big units together. But there is another question, which is the transistor is eventually it is on a piece of silicon. You're just dropping, you're basically scooping some, doping some silicon to some depth, and the transistor is still there. It's 2.5D is what's called. It's not fully 3D. There is a lot of research going on to basically make the transistors, more and more, to the point where, the part that is conducting is completely surrounded by the dopant or the other material, the gate. And so what we have is like basically you have the sources and the sink, which is, one with a surplus of ions and one with a deficit. And then you have a gate, which is on top of, which can, switch on and off. But then the question is, can the source and sink are at two corners.
Right.
And the gate is also like just on top. Can it be such that the gate completely covers and the source and sink are just at one corner? If you imagine a pipe, can basically gate completely cover the whole thing? So then you can make the transistors way more efficient. And that isn't there today.
Right. So I think this would require a visual for us to understand. So I've also heard of something called 3D stacking. So is that a completely different concept? 3D stacking of chips. So that's another area of research.
Yeah, that is yet another thing. Yes, that's a very good point. And that comes at the packaging level. So today, or not today. So today, if you today, you have chips in market with Intel Sapphire Rapids, which is 3D stacked already. But if you go back even 1 year ago, you basically, if I talk about your SoC or take your phone as an example, all of these all the chips that form your system in your phone are all you have a motherboard and everything just plugs onto that. So you stick it here, stick it there, stick it here, and it's all 2D. And then this motherboard does the job of, talking between these different chips, and that's through a substrate where there are wires and wires in the substrate, and there are pins. You slot onto these pins in the motherboard, and these wires can, these pins can talk to each other, and that's how they were initially designed to talk. But as you have more and more chips in your system, you need to communicate faster and faster between them. So, and this became a bottleneck, and that's when 3D stacking became a thing, where it's a pretty it goes into this realm called packaging, and packaging is another area where actually Intel is a big is one of the most advanced, and it's all about can you put chip on top of chip on top of chip. And this is one example where the blue part that you see in the center is called a through silicon via, because it's going through silicon and between different silicon layers, and it's a via for viaduct. So it's basically imagine a fat pillar which just connects all these chips together. So what you can do now is you can mix and match technologies. You can have memory at one technology, you can have logic at one technology, you can have IO at another technology. And this fat viaduct in between is like this wire, which allows you to communicate at terabytes a second of bandwidth. So you can very quickly communicate without having to spread them across a motherboard with this fat thing, which allows you to all these chips to talk together.
Got it.
Yeah, this is like an elevator that's connecting multiple floors of a building at very high throughput or something, right?
Yeah. Yes. And I was actually involved, deeply in the manufacturing of this giant pillar in between. Wow. It's a nightmare, because you can imagine that transistors are little, tiny specks of metal in everything, and this is what giant slab of straight up, whatever fancy metal is being used. It absolutely screws up the density. So it is very hard to manufacture that, because you have in the entire current characteristics, you have raw current flowing through all of this giant wire, and it has an enormous amount of inductance and capacitance that it generates, and it just messes up everything around it. So you have to do a lot of clever manufacturing to account for this massive change in density, where you have so much metal all piled up in one place, and then you've just bits and pieces of the transistor metals away from it. So it is a challenge to manufacture. This particular via.
That's amazing.
I see.
Yeah, so let's get to, I think we have been talking about state of the art in general chip design, right?
Yeah.
But something that we wanted to deep dive with you is applications to AI, right? So what are the chips that are being developed for AI models, training neural networks, for instance? So tell us a bit more about that.
Sure. So what the few things economically, technologically, which has resulted, and math, which resulted in this. The math was basically figuring out that for all of its jazz, a lot of AI is just multiplying matrices. And that is the first problem to fix. And then other things follow after that. And the second thing was like, okay, once you've done this, you've kind of restricted your math. So you can like start creating custom logic for it. Second thing is that the tools have improved a lot to the point that you can have a 15-20% company absolutely capable of, coming up with a hardware design, creating this design, handing it off to a contract manufacturer like TSMC and get fabrication done. You don't need capital investment of billions of dollars. You need capital investment of about $5 million to $6 million to come up with a prototype chip today.
I see.
And the third thing was this thing that, AI is so expensive in terms of the number of mathematical operations that are required to get an answer from your image to your, to all the detections, or from your, prompt in ChatGPT to the text that it produces, that it played this demand like no company serving it is capable of basically it would just blow up the cost. So Google basically saved the equivalent of dozen data centers of cost by creating their own chip. Mm-hmm. So and they just absolutely they did this massive vertical integration. So whenever we think of anything, the first thing is performance. So imagine these players, they want more and more performance. So, either faster serving of your, quickly responding to your queries, or, doing the same thing at a lower dollar spend. So that is the fundamental thing driving everything. So behind that comes like, okay, what can we do? And the fourth thing I should add was like, the spectacular drop in interest rates that we saw till recently, which allowed a lot of money to be invested into the space to try and come up with newer solutions. So these 4 or 5 things together created this Cambrian explosion of all sorts of architectures, chip designs. There is like Google came up with its custom chip called the Tensor Processing Unit, TPU. Right. NVIDIA already had its graphic processing unit called the GPU. GraphCore had something called the IPU, for which they call as the Intelligence Processing Unit, and then FPGAs are always like the very flexible, where you can pretty much decide whatever you want to build. You can build any kind of logic into them, but more inefficiently. So FPGA, you can control it at the transistor level, but the challenge is that it is very, very inefficient. So it allows you to experiment with all sorts of hardware designs. And the only people I know who are using FPGAs today is Microsoft. There is an adage in the industry that if you're using FPGAs, you don't know what you're doing. So no ding at Microsoft, but it is it's everybody else tries to make real ASICs, like and the word we use is called, we bake the ASIC. We freeze a design, and once we know what we're doing, we stop using FPGAs and create a full chip just with that. Go on.
So just to go on this, so I think everybody understands CPU. So when we're buying computers, so could you take us through CPU? What does it stand for? GPU? What does it stand for? And what are the key differences?
Yeah, so CPUs, the central unit which does the math, was always like, it started off just a scalar unit. Going long back, it was always called the ALU, the arithmetic and the logical unit, which would take like two numbers, either add them, subtract them, or do a logical operation on them and return. Then it evolved to vectors. So you had a vector of units here, and you could take a vector of inputs and a vector of outputs, or vector of two inputs, take their dot product, take their cross product, or do a bunch of operations, which are all vectors. What changed with
for the uninitiated, a vector is the same as a matrix?
No, vector is a one-dimensional matrix. So when you have just a single line of us.
Okay.
Yeah, a scalar is a single number, a vector is a line of numbers, and a matrix is a square rectangle of numbers. That's how.
So array of numbers, and then two-dimensional array is what you're talking about.
Two-dimensional array of numbers is a matrix.
Okay.
And what changed with AI was basically, and GPUs for a long time were just vector, just brought in vector processing into it. Eventually, CPUs caught up. CPUs also brought in vector processing and so on. But what changed with AI was this arrival of this realization that, hey, we are just multiplying matrices. Matrix multiplication is a very big. It's a very big component of the whole thing. So in this ALU, people started basically. That's a good schematic. So GPUs had a bunch of of these vector units that were just they were used for processing. But with with AI, basically these ALUs became like matrix multiplication units baked into silicon. So you have silicon units which are just there to multiply matrices. They have fixed unit sizes, and that's how GPUs differ from TPUs and so on. But these units, it becomes very simple to program. Just you have you're mathematically you have your at software level you have a big matrix defined. Break it up into these little blocks and just feed that into the chip, and it will multiply it all by itself and just get you the answer. And,
so maybe a few things, right? For just to make sure we clarify and expand on.
Yeah.
So GPU is a graphics processing unit. So when I buy a computer that has a gaming laptop or gaming PC, that NVIDIA graphics card is essentially the GPU, right?
That is historic. That's how the name comes. Yes,
okay.
But there is nothing about that which makes it really good for AI today. So what makes it really good for AI is the presence of these special units in a GPU called as tensor cores. And these tensor cores are what they contain these matrix multipliers. And these tensor cores started off in the GPU and the TPU. TPU also contains tensor cores. And as of today, even CPUs have started containing tensor cores. So with Sapphire Rapids, which is Intel's latest product, they've also started putting that into the CPU. So everything now has tensor cores. So they all can do AI much faster than they could do before. It's all the question of what do they choose? So the TPU is like the biggest, baddest. It chooses like a giant block of 512 times 512. That's the size of a multiplier. This consumes so much power that a TPU can take only 2 of these blocks into one single chip. And before it maxes out on the power, it already hits 400 plus watts per chip. A GPU has, I think, if I remember, about 32 by 32. These are smaller blocks. CPUs today, the ones that have come out, are in the 8 by 8 regime. Imagine, as you add bigger blocks, it just consumes more and more power. It also means that, you're investing a lot of silicon into just doing one thing correctly. And that is both the advantage and the disadvantage of TPUs and CPUs and GPUs. But GPUs are trying to choose this balance where, hey, I can do other things. CPUs are saying, I still have to support the Zoom call that you're doing. I still have to support a spreadsheet. So I cannot be burning this much power just to, have these blocks which multiply matrices. TPUs are like, I define all my AI just to be big models, and they will multiply matrices more efficiently than anyone else. But that forces you into this hammer nail kind of a problem where TPUs force your models to be big. Google, that's what they've done, which is they've just customized their models to be more and more TPU friendly. And TPU does matrix multiplication very well, but it does little else well outside it. So that is Google's managed to pull it off so far. But that's also one reason why you don't find TPUs being sold externally. So they abstract it through a cloud. You don't know what's happening in there. You don't know what it can do well, what it cannot do well. Is behind layers and layers of software. GPUs do things pretty flexibly, which is why anybody can buy them. They're free to hack into it, free to find out whatever what it does. And but that's the flexibility that they build in. I think they have a good balance of doing all sorts of AI today.
So it looks like, to summarize, so CPU started off by simple calculations, right? The scalar multiplication. Right. So 2 times 2. And then GPUs are all about vectors. So that's why they were used a lot in video games, because it's all vector processing, right? The graphics is a lot of vectors. And now we are coming to AI applications, which is all about matrix multiplications and linear algebra. And that's when TPUs are becoming, I guess, in some sense suited for that. Is that a nice way to put it?
That is a nice way to put it, but I'll just add one more thing. If anybody has to supply a chip that does AI, they all need matrix multipliers. So GPUs have tensor cores, GPU have matrix multipliers, and even CPUs today have I've started having matrix multipliers now. So nobody can be away from it anymore if you want to do any kind of AI in it.
Right.
MacBook Pros, your latest Apple Silicon, they also have if you have the latest M1 silicons.
Right.
They have matrix multiplier units in them.
I see.
And maybe I think just to add one line, I think on GPU, why GPUs have had matrix multipliers in the past. I think this is, again, I'm dating myself now. It's like 15 years ago working on this topic. The idea I think at that time was that every pixel on the screen, you can imagine your entire screen output as a matrix. And so every pixel that you're seeing on the screen, so let's say you have a 1024 by 768, which was a standard or cutting edge screen back then, was essentially a matrix of that size. So the graphics processing unit has to compute a value for the RGB channel, which is red, green, blue, which is the three kind of pixels that make any given pixel, to decide what image is being shown on the screen. So it's essentially computing the equivalent of a 1024 by 768, three of those matrices, and that needs to be done at the refresh rate of the monitor, which usually, let's say, is about 24 frames a second for you to perceive it as video. So you're talking about a pretty large level of matrix calculations that need to be done, which is why GPUs have been historically good at matrix multiplication. And then I think it was this happy coincidence of us figuring out when we started building neural networks that we modeled neural networks as matrices as well, and then found that there was this bunch of hardware lying around that was very well suited to matrix manipulation. And that's when the happy magic or marriage happened. Terrible for gamers, because I never find the GPU that I need, because all you AI scientists come and buy up everything that's on the market, so I'm not able to play the games that I want to play. But I guess very good for human civilization in general, that like we found a very nice hardware that melts with the software.
And the tensor core I was mentioning was when they decided they're just going to bake it into silicon. It's just going to be like part. And what is meant by baking into silicon is that even if you're not doing neural nets, you're burning the power for it. Because that logic is kept alive all the time. If you don't have it in silicon, it's at software you decide whether you want to run matrix or matrix multiplication or not. But you're not you're not always permanently burning power for opening a spreadsheet. So that's big.
You're saying like baking it is like leaving a car's ignition always on 24 hours a day, 365 days a year, even if you're not driving the car. Versus this other thing where you like switch on the car and drive it when you want to go, and you turn off the engine when you're not using it. That's like the equivalent.
No, I would rather call it like if you have a car, you're also carrying all the steel that comes with it and all the wheels that come with it and everything. So if you decide to add more features inside the car, if you decide to have a giant 8K monitor inside a car, heavy, some fancy entertainment system, it's going to be in the car, traveling with you wherever you go, whether you use it or not. So that's what I meant by you're baking it into silicon.
So it's like trailer, right? So you can have a trailer that can carry more stuff. Do I attach the trailer to my car, or do I attach it only when needed? Right?
Got it.
So it's like
permanently attached trailer
that's very heavy.
you cannot disengage, and it's like permanently. Got it.
But if you decide to always move heavy stuff, it's very useful. It's very efficient, but it's also useless when you're doing other things.
Right. Like going to the.
I think we have a lot of analogies for that now.
I love it.
Right.
Great. So coming back to, I think, some of the recent technologies. So you mentioned something about some of the exotic hardwares, right? So Cerebras, of course, we talked about that. Could you touch upon GraphCore and D-Matrix and how these things are compared with each other?
Yeah, so GraphCore, the company I used to work for, had a different bet. The bet was that it is basically saying, so if you go deep into what makes GPUs really attractive today, it's this memory, and it's a combination of memory and compute.
Right.
So GPUs come with their own private, own attached memory that they have. and this memory is called it's called as HBM, or high bandwidth memory. And what it's there's only one company which manufactures it, and that's Samsung. And this is very, very expensive, but it basically gives you memory at high bandwidth. So as a point of comparison, your standard memory modules that you attach in a CPU give you about 200 gigs a second in high-end CPUs, very high-end, like in server-grade CPUs.
200 gigabytes per second of memory transfer, right?
Memory transfer, correct. And the thing is, once if you start doing your compute very fast, if you take your matrix mults and just like smack it with raw silicon and do it very fast, you're left like you starve. You're basically waiting on memory to data to come, and you've had this problem where the first order problem is gone, but the second order problem is okay. Now I just need data coming fast enough for me to at the rate at which I'm consuming it, and that's why you need it.
So GPT, let's say GPT chat, right? So suppose GPT chat is creating this sequence of text, but then it needs to be, printed on a paper and then sent it outside. Then it's like, hey, there's no point making GPT faster if paper is the place.
Paper is the bottleneck.
Right. Right. Got it.
Exactly. So once HBM basically gave you a lot of bandwidth, and that allowed you to, and that was required for tensor cores. So once you started putting these kind of units in, you needed proportionately fast memory to keep the whole thing going. But the biggest problem with HBM, and which is what like today, NVIDIA is always grappling with, is it is hard to increase capacity. The best HBMs today get you about capacity of 80 gigs,
right?
And bandwidth of about 2 terabytes a second. So 5 times, so 2,000 gigabytes a second, and capacity of 80 gigs. Now, take GPT-3 as an example. It has 175 billion parameters. So if each parameter, each weight took 16 bytes, so two words, that's already 350 gigs of storage. So you cannot fit that in one GPU. You need at least 4 to 8 GPUs to start squeezing that in.
Gigabytes. So that's the official number. 800 gigabytes.
Exactly.
So that, right.
So you need automatically that many GPUs before you can start just fitting to serve you your requests. Just to fit the model, you need that many GPUs.
It's not even training; it's just inferring. It's just running.
Inferring. Yeah. So it's just to fit it in. That many GPUs are gone. So that's so GraphCore came with a bet that hey, let's go back to if we start increasing the amount of SRAM in a chip. SRAM is what is called as cache and other things. Like today in a laptop, for example, you have 12 megs of SRAM. You have broken into L1, L2, L3 caches. This is a standard CPU terminology. GraphCore came with the thing that I will give you 1 gigabyte of that, which is imagine 12 megs and this is 1 gig. But if we give you 1 gig, you're going to be so busy utilizing the 1 gig that I can then connect it to low bandwidth memory. You can live with 100 gigs a second, and 100 gigs a second is commodity memory modules, which is used everywhere in the world, and you can scale that independently to terabytes of storage. So your capacity can go up to terabytes while you're, because you've allowed for much lower bandwidth. And why lower bandwidth is because I've basically given you, even though if you have tensor cores, I've given you so much SRAM, so much cache, it's basically a giant pizza to eat. So by the time you start eating, finish the pizza, even though my delivery is really, really slow, I will reach that before you finish eating your pizza.
Right.
So that was the basic thing, saying it has a lot of compute, but it's this memory that you see. The AI memory is about 3.6 terabytes. So it gives you a lot more memory, but the catch is there's a trick here, which is you have lots of SRAM, and the aim is to accommodate all that live computation within that large SRAM. The jury is out whether this is fundamentally a successful idea or not. the idea harks back to very standard computer science that you need. If you have a lot of cache, you can go with very slow main memories. But it's the same analogy, right? If Ford had millions of chips for its computers, stored it in its inventory, it would care less about what's happening in the outside world, about whether there are supply chain shortages or not, because it has so much in cache. By the time it consumes all its chips, COVID can come and COVID can go, and then the factory can completely start you're not exposed to the vagaries of the world economy if you have enough cache, enough storage, or enough inventory.
Right.
It's and this was the bet, but AI is growing so fast that I think most people are coming down to this idea that you absolutely need high bandwidth and high capacity, which is two very opposite problems. You can give one, you can't give the other usually. And all of the advancements that NVIDIA, AMD, anyone in architecture is doing is to address this one-on-one problem. How do you give high capacity and high bandwidth memory together? I think the problem of compute is largely solved in AI hardware. Everybody knows it's tensor cores. Everybody has them. The only question is, can you give a lot of memory at very high speeds? And that is kind of what we're grappling with today. Multi-chip packages, more HBM stacks, and today, what people are thinking about is a couple CPU GPU, where you don't have a CPU and a CPU as separate chips, but you're building that logic and tying them up very, very close to each other. So you basically have the capacity of a CPU, and the entire memory of the GPU then just becomes an inventory, becomes a cache.
Right.
And then you're very quickly pulling from that and then feeding the GPU. So that's where all the latest advancements are. It's can you pull from the CPU's main memory fast enough, and can you use the GPU as a cache, GPU's memory as a cache, so that you're able to hide this entire provide capacity and bandwidth. It's again a standard problem. Like for example, if Netflix is giving you movies, it would keep the movies you watch more frequently close to you, rather than a data center very, very far away. It's the most logical next step. It's not a fundamental revolution.
Sure.
So they're all doing the logical next steps.
It looks like all these these fights are still based in silicon and semiconductors. But I would also be interested to learn more about some of the other types, right? So photonics, for instance. So how do they fit into this whole field?
Yes, that is very interesting. So photonics is what is calling the revolution. It's fundamentally capable of providing high bandwidth at and high capacity together. And the way it does it is it completely removes wires. You have lasers communicating. You basically switches, which are always you have some data here which is digital. Then you have a transducer which converts that into pulses of laser. Like as the data is being read, the laser turns on or off. And then you have another thing where that laser, that input is received, and that's converted back into digital. So the chip is all digital, the storage is all digital, and then it's just the connection between them, which is now just through lasers. So
interesting. So the transistors are still semiconductor, the silicon based, right?
Yeah.
So wires that we are replacing by photonic connections. Is that?
Yes, that is exactly the thing. So at the boundary of the chip, you have this sea of transceivers, which basically are analog to digital or digital to analog converters. And that is the new bottleneck. It's easy to send a bit, by laser and receive it, but the question is how quickly can you do this digital to analog process? And that's where all the challenges of photonics are today. Which is, can you do it fast enough so that that is not the new bottleneck? It should still be faster than just sending it by wire.
Take the analogy in the real world. So you have these, typical wired cables to transmit information. Now coming up with optical fiber cables, right? So it's the analogy.
Yes. These are actually optical fiber cables, just a little more advanced. These are fundamentally optical fibers. And it can be a bundle of fibers, or it can be any which way you want, but they're fundamentally optical fibers. Question is, how quickly do you optical fibers, while it's going through the fiber, is capable of a certain bandwidth, but the bandwidth at the end, when you convert that back into digital, is much, much lower today. That needs to be overcome to be able to make it useful for chips.
So what problem is this solving? I didn't follow. So is there still a physical cable or there is no cable?
You can choose. You can actually have physical cables, or you can just have, the laser inside the cable, or you can have lasers outside. It's up to you. Most people would prefer.
Yeah, but if you have laser outside, I'm trying to build this picture in my head. So you're saying there is a chip and there's a bunch of lasers being shot off right above the chip that are communicating signals to each other. Won't that just be like massive signal interference and all sorts of crazy stuff going on? They're all like sending.
Yeah, the brilliance is that, like, imagine even if it's just one cable, all these things could be at different frequencies, so they don't interfere.
Oh, okay. So like different frequencies of light.
Yeah, different frequencies of light, so they don't interfere with each other.
So one is just reading, it's reading the violet.
Red light, green light, yellow light, and they're far enough that they don't. They're not close to each other.
Okay.
But no light is typically exactly one wavelength. It's like a Gaussian. So as long as they are spread enough from each other, they're not going to interfere. They can go through each other with no problem.
Yeah, but the problem you're solving is that you're saying the speed of interconnectivity on the chip itself is too slow?
No, but it's between the chip and the memory. So wherever you're storing your model and storing the data, that getting that data quickly enough has become the new challenge. It's become exceptionally acute with the ChatGPT kind of models, where you're predicting it literally alphabet by, character by character. It's not, or sometimes like one word at a time, not more than that. So word at a time. And it's not that it's predicting the whole thing. So you predict one word. Based on that word, it predicts the next word and the next word. So a lot of back and forth going, between, by the time you boil that down to what's happening on the chip. Yeah.
And
so what is the back and forth?
Optical fiber cable to get speed of light.
Yeah. Right. So the back and forth is that you basically, every word has to go again through the entire model to give you the next word. So if you have predicted 2 words, both those words then go through the entire model, then to get the third word. It's not that you send your input once through the model and you have all of the output, which is the standard way of imagining. So if your entire model was just like, here's my input, all I'm saying is true, false, or something, you're sending the input once. But what's happening in the generative models is that the model is changing. I mean, your output depends on what you've just produced, like the previous words. Exactly. So as you're generating words, your next word is responding to that. So you're going through the model. Every single word involves another, loop through the model.
So when you say loop through the model, you're saying that the model has to be fully loaded into memory every single time. And that's what you said is not even possible on one core. It has to happen on like multiple GPUs.
Let's say 8 GPUs today. Yeah.
So, and then the input and the model are being cycled through the entire memory for every additional word.
So the input goes once. Okay. Then you have all of the input produces one word.
Every output is like, at the end of the day, is
that one word then joins the input and becomes a new input, which goes all the way through the model again. So it's not that you've gone into your first GPU, come out of your 8th GPU, and you give it to the user.
Gotcha.
You have to go through this thing, every single word, like several times. The loop has to be completed.
The reason for that is every additional word generated now has changed the state of the input, and therefore
that becomes the new input. The new input
is the earlier input until now plus this new word that I've generated, and I have to do this for every new word that I generate.
Yes.
That's insane. Like, that's not how humans think at all, by the way. I mean, I don't think so. Like,
absolutely. You think of the answer and you put a sentence around it. But, this one, like, is just creating, like, imagine you're going word by word and creating your answer on the fly. And that generates insane requirements on the entire memory stack, which is what these photonic startups are trying to address. There is also others that people are trying to do the entire, matrix multiplications using lasers. By the interference is equal to addition or sum. Sum is equal. So they just change the phase of the same frequency. When you change the phase by enough number, you can always have 2 waves cancel each other. So that becomes like like a subtraction of two things.
Right.
So if you have exactly the same phase, they become addition. So once you have addition, subtraction, and then enough adds becomes a multiply, and then you can pretty much get all of everything, all of arithmetic happening just through lasers. But some startups are trying that. It is still not clear whether they will succeed. If it is, like, that's another massive revolution, because it will cut down the power or increase the speed of computations enormously, because you can have so many frequencies, lasers operating in parallel, doing all your different, multiplications. It just blows up. It's mind-blowing, the number of things that can be done if it works.
I thought like lasers on lightsabers in Star Wars were cool, but now you're talking about those lightsabers doing math while Darth Vader and Luke Skywalker are fighting. That's a pretty crazy image.
But they all deal with one fundamental problem, which is lasers are very sensitive to temperature. So what Star Wars doesn't like you to show, if it's hot, Luke Skywalker's saber might actually be shorter.
What?
If he's in a cold planet, his thing might be longer. And they don't talk about temperature effects, but temperature effects are a serious problem when you're doing AI, because your answers can keep changing whether the chip is hot or not. And then you cannot expect like results to depend on whether the day was, it's a hot day, so I'm going to tell you that all the cats are actually dogs, and it's a cold day, so all the cats now become mice. So you can't expect, that is unacceptable. So they have like these kind of physical things to deal with.
You're saying this is like a turtle egg, where I believe like the gender of a turtle egg is dependent on the temperature in which the egg hatches.
Oh yeah,
at certain temperatures you get females, and this is the problem with global warming, where like a bunch of turtles were just, I think, turning out male or something, and that's therefore like extinction. You're telling me the cutting edge of AI is like a turtle egg that's dependent on the temperature at which
if you go lasers, if you go using lasers for math, if you stay off that, and then you're fine. Like digital logic is reliable and consistent. It does not depend on temperature.
But one thing that all this like brings up is that we talk about, like blockchain being horrible for the environment. But what you're describing is even this AI stuff, ChatGPT, is probably terrible in terms of power consumption and like heat generation.
It's enormous. It's just absolutely horrendous in terms of the resources it consumes, which is why there is a massive
But I have a different
demand to really make it faster. Yeah, go on to that.
No, I have a different take in general, right? Like, hey, you're making something, you're training this one computer once, and then inferring is relatively easier, versus somebody driving 20 miles and sitting in an office in front of a computer and then doing the same work for a day, right? So, I guess it's a debate that we can have.
But AI, models will become bigger before they become smaller. There is no way we can economically sustain these kind of big models. They will grow bigger, and when people figure out, okay, what is this is a working formula, they will aggressively shrink it to something which is not this expensive anymore.
Makes sense. Like something like brain, right? So we have the brain, human brain, which has a trillion, 100 billion neurons, but then we only use about 10% of it. So we will build the entire thing and then figure out, hey, which parts are needed, and then I guess compress the remaining parts and so on. So probably that's the direction that we're going.
But what this means, Bundy and Mrinal, maybe we've talked about carbon credits capture and trading of carbon credits, right? Like maybe there's a future view where like the computation itself becomes now a constraint, not because of any other reason outside of the environment. And now companies have to figure out how to really ration how much compute you throw at what given problem. And maybe you can figure out how humans also have to trade this, because I know feel terrible about like going and ask ChatGPT to come up with like a stupid poem about a cat. Maybe it's like, I don't know, consume like the power equivalent of a city in like Asia or something.
That is interesting. And there are two answers here. One is that data centers are trying to go green, where as long as it's going to a data center and they power it with renewable resources, you are then less need to be less worried about what's the environmental impact. But there's also AI is also to be personalized going into your device. So your phone and your laptop will have AI smarts. Now, does Apple pay the carbon price of its manufacturing or the carbon price of all that the laptops burn?
Right.
Because they're putting all this big ass silicon into your phones and laptops, and that's going to keep running. And so what is okay, so to be personalized and to be, for privacy, AI is going to go on device. When it goes on device, like the devices have to get like far more beefy.
Yeah.
Now, who is like talking about where is the carbon, the price coming in? Is it with the company or with the consumer? I don't know.
Great question.
No,
Exciting times.
I think it's a good segue into going from tech to other aspects of the business, right? So something that I'm very curious about is the whole economics of it. So we have touched upon the carbon economics of it, but just thinking about the pricing, even how this industry is organized. For example, I wanted to learn more about the contract manufacturers and how do they work and how does this fit into the entire ecosystem?
Yeah. So the biggest contract manufacturer today is TSMC, as we touched upon, Taiwanese semiconductor manufacturing, and then there is of course Foxconn, which does a lot of the other later assembly work once the chips made. But then typically, like if you go back 20-15 years, all of manufacturing was done by Intel and AMD. They made the chips, they designed the chips, they manufactured the chips. They had this entire vertically integrated business.
Right.
Everything they did was tightly coupled. They would make designs which are only manufacturable. They will not go outside that.
Yeah, when I was in my undergrad, the only decision that I had to make was, hey, is it an Intel computer or an AMD computer?
AMD computer, exactly.
Fedora core used to work well on AMD, Ubuntu on Intel, things used to be very simple then.
Yeah. And these were the only ones manufacturing, and TSMC was not as good. But what the magic which has happened over the last, it's actually just 3-4 years where this has happened. Intel was always like a generation or two ahead of TSMC, mostly because it could tweak its manufacturing. And when I was in the factory, we did the same thing where we canceled the designs if they were hard to manufacture. So if there were particular designs which reduce this thing, we would tell the designers, go fix it, go change it.
Right.
Because, it's logically perfect, but it just it's a pain to manufacture. So TSMC was always fighting with, one hand behind its back, because it said, I can manufacture anything. Like, I'll give you a rule book, and as long as you stick to the rule book, I guarantee you I'll do anything. And the fact that they could do it, fight with one arm behind their back, and produce good quality chips, basically allowed Apple to start designing its own chips.
I see.
And Apple started then gearing its chips to its software. So the apps that run on the iPhone, or the most popular apps, will be given priority to become more and more efficient, and it will design its its logic to basically make these apps go even faster. For example, Uber, if you run it on a very old iPhone, will just kill the battery. But if you run it on a new iPhone, it will run for long, because these apps have been always optimized on Apple Silicon to make sure they're always running really well. So they were able to separate that out and start giving their designs over to TSMC to do it. So today, Apple, NVIDIA, Qualcomm, all the big, these huge players all go to TSMC for manufacturing. TSMC will come up with a rule book, and it's called the design rule book. And then you have to, honor that. And then that's it. They will make sure it works.
I see.
So
magic happened. Yeah.
You're seeing the success of the iPhone and Apple's decision to build its own silicon that has led to the rise of TSMC, if I understand what you're saying.
It's the other way, which the rise of TSMC to be as good allowed Apple to leave Intel and start making its own chips.
Interesting.
I see.
And not be forced.
Look at the market cap, right? This is something, this is only last 5 years. So Intel has been just flat 200 billion.
Yeah.
The growth of TSMC. I mean, this is something that should get heads rolling, right?
It has got heads rolling. It has, and the thing, I mean, what always happened within, and I was at the era in Intel when you see this divergence to happen. I was in the factory right when this divergence happened. People used to, Intel used to convince itself saying, this is, we have hit the limits of physics. So, if we are slowing, everybody's slowing, no big deal. We're still like the generation ahead. What happened, when you start seeing the stock, diverge is also the point when TSMC actually started beating Intel. And it started going ahead in manufacturing technology. Right. It had never happened before that. And, given like how they're not like a fully, they're a contract manufacturer. They don't know the designs that come to them. They don't know the applications. They don't know those kind of things. So they just operate off a rule book. So, and the fact that they were able to beat Intel changed the industry in such massive ways. Wow. The fact that you have an M1 silicon in your MacBook is a direct consequence of this. The fact that NVIDIA is so good in terms of its capabilities is one of the consequences. The fact that you have Qualcomm and producing all this is a direct consequence. The fact that AMD, which used to be always like a second fiddle, caught up so much with Intel was because they became design equal to Intel, and now they have better manufacturing technology that they can depend upon. So they are completely eating into Intel's data center business because of this.
Right. Like two very interesting things, right? I think one timeline wise, I think 2020 is when Apple Silicon gets released, like for the iPhone, for the Mac, and a bunch of like things together. That's I think where in that chart, Chaitanya, like the TSMC market cap starts to like really start to hockey stick. Right. And the other interesting thing is, it seems like then, Mrinal, from what you're describing, it's like America's lost its competitive edge over the last few years. So the CHIPS Act, that's
2 years.
Just 2 years. Literally last few years. It's very recent, but you can see the impact. How, on product, it's such a dramatic impact because people. Intel could always ensure that everybody can design as well as me, but I can manufacture better than y'all. So overall, my chip is better. But that the moment it changed, suddenly you had an explosion of other providers, all having equal or better designs than Intel.
Yeah.
So this CHIPS Act,
that is what allowed
This is so dramatic, right? So chips being such an important part of the AI revolution, right? And this should be a much bigger story than, hey, it's just an Intel staying flat versus this tripled. And especially in Taiwan, which is going to be I guess, we'll go into the geopolitics now. So this explains why it has become such a hot issue now.
Nancy Pelosi's visit to Taiwan now takes on a whole new meaning when you look at this chart. It's not just posturing. It's like security of the United States at some level.
Yes.
It's linked to this.
Absolutely. Which geopolitics-wise, Taiwan says, what they have is not. They don't need a missile defense. What they have is a silicon shield, and their silicon shield is basically TSMC. The presence of TSMC ensures that the world will come and save Taiwan, because if without which all of the silicon basically the industries and all of the advanced economies just grind to a complete halt. Because if TSMC's factory is invaded and occupied, that's a chip stop. And then you can just imagine the massive ramifications on everything, because we are in a highly automated economy. Without a continuous improvement in chips, we're in a deep problem.
Yeah, so just to understand that a bit more, would it not be good for Intel?
Oh, sorry. No, Chetan, I was just saying that chips are almost like the new oil, right? As an oil-producing country, that countries will come to your aid in case of an attack because oil is the foundation of the economy. You're almost saying that silicon shield is the same thing in the 21st century.
Right.
Pretty much. It's Saudi Arabia in 1990 when, Kuwait in 1990 when basically Saddam threatens it, the world comes to its rescue. They honestly don't care about Kuwait as much as its oil. It's the same thing with Taiwan. The world will come to its rescue. If the challenge, of course, it's China. It's not Iraq versus Kuwait. Completely militarily weak countries attacking each other. But this is another added complexity.
It's even bigger risk, right? So now you're going after going against another world power, right? So it's.
Yeah.
Right. Hey, Chetan, you had a question though. I think you were.
I was just gonna say. So the difference from chips being the oil, right? So oil is physically restricted to be there. So one thing that I wanted to understand was what's the question that I had asked some time back. So take the TSMC factory, just airlift it and put it in Texas. So what's stopping that?
Copy exact is very, very hard. So you need a lot of, you need some time, like, several $1 billion where the factory is set up and it's just producing junk before it catches up with the capability of its Taiwan factory and all the supply chain of all the chemicals, the equipment, everything to be set up. And that is something that TSMC is very unwilling to spend. So that's where the subsidies come in. They're like, we're happy to do it, but you pay for, all this downtime. Because economically, it makes no sense to me, because I will continue investing more into Taiwan and just making the factories even bigger. And so if you want me to take an uneconomic decision, pay for it, pay for my factories.
If they're willing to spend billions of dollars in, in one place, right? So they should, this should be a no-brainer, I guess, right?
Yeah.
That's what the CHIPS Act is probably trying to do, right? It's trying to attract
CHIPS
investment.
Act is exactly subsidizing all of these things so that people can come back.
It's to reverse Chaitanya's chart. I think it's to make Intel some American company back in the leader in this business.
I don't think the chart will reverse because it's mostly to get the chart will actually expand even more. They're basically telling TSMC to come and set up a factory here. So TSMC makes more money. It's not going to, it's not about making Intel catch up. It's just saying TSMC, you guys can be the most profitable. You're fine. You can continue beating Intel, but make your chips here, because if your Taiwan factory is occupied, you're still producing something here which is going to feed my country.
I guess it looks like it will happen at some point.
It is going to happen. Yeah.
So, this just we have just been talking about TSMC versus Intel, right? So where do the other players fit in? NVIDIA, Google, the Oracles of the world. So, how are Google, right? So how are they thinking about these things?
So Google, of course, manufactures from TSMC, or they all manufacture from TSMC. They're in a different space. So if you have your chip, the question is, what can you do? And Google has the story of being vertically integrated for everything except manufacturing. So it designs the chips, it has its manufacturing hub, it's got its own chips, it's got its own data centers, and it's got its own software, AI software. And what it's then trying to do is basically, can I then just serve AI through the cloud? But since I own the entire stack, can I come up with a much cheaper alternative than my competition?
Right.
And that's been Google's strategy throughout. It created the software framework TensorFlow. It has TPUs. It has Google Cloud. They all exist to basically feed one story, that if you use AI, you do it through Google's cloud.
I see.
You get the best price and the best models and best everything.
Right.
And their AI first investment was to make a vertically integrated AI company.
I see. Got it. Right. And who's making TPUs, by the way? Is it TSMC as well, or?
Yeah. TPUs is fabricated by TSMC. Everything is everything except Intel's chips. And the really embarrassing part is some of Intel's chips are also being manufactured in TSMC.
Wow.
Because they are struggling with delays, and their own process not being good enough. And they're like, I cannot lose market share, so I will also go to TSMC and manufacture it there. And it is like a real egg in the face for Intel.
The other thing I understand, Chaitanya, the chart that you showed, that's what I still can't get my head around this. Mm-hmm. It's not like they sunk billions of dollars into R&D or something. How did suddenly in that 3 year, what? It seems like this is a huge story, right? That we're not just learning about. How did that happen? Because the hockey stick happens after 2020. That's obviously the pandemic and everything. But the investment wise, Intel has been sinking money as well, right? It's not like the red bar on the left has dwarfed.
It is the realization. There are three factors at play. The first is the realization from investors that Intel is not catching up till 2023, 2024. Because Intel's been claiming every year that it's going to catch up with TSMC. And then it announces 1 year goes and there's a delay. Oh, there's another delay. And this is where investors have realized that it is not catching up. Second factor is...
Even before catching up though, my point is how did TSMC even get ahead? It's just...
that is... I wish people do a documentary on how TSMC... here's a joke, okay? If you talk to any Taiwanese immigrant in the US, they will say that anyone who came first in class came to the US. Anyone who came in the middle rung, anyone who came in last went into the army, and anyone who was in the middle, the average mediocre, went into TSMC. And the remarkable thing is, that's a joke. That's a complete joke. Okay, this is just anecdotal. These are like jokes you hear, floating around. It's not reflective. But then with this thing, they still managed to produce a company which is absolutely world beating. In the hardest of the hardest technology, we talked about how hard it is to manufacture, and they are actually taking a lead. They took the lead, and now people have realized that the lead is there to stay. It's not going to be covered anytime soon. So that's when, it's a remarkable growth of, what TSMC's pulled off is just humongous.
So while in the US, we were busy with the culture wars. Hey, should I go to office? Should I vaccinate myself? And, should I commute or just work from home? When all of this was being discussed, so TSMC was just chipping away, right? So that's the chart's name.
Yeah. And also during the pandemic, right? They were able to, they shut down they quarantined the entire island out, the country out. The factories were running 24/7 all the time, and the total production they were doing just exploded. So they sold more. Their competition was nowhere in sight, and they have this lead that is going to be maintained for several more years. And that is when people realize they have a monopoly. Samsung has the same monopoly in memory. TSMC has it in logic. And these are the two things which create AI. So NVIDIA's chips is logic plus memory. And that's, you see, then the realization that, oh my gosh, these companies should be worth way more than they are.
Right.
Boom.
Right. Yeah.
This is such, it's the story of 3 years, like 19, 20, 21. That's when I think you see that little bar on the red bar on the left starting to really rise.
Yeah.
And then it's a lead time of about a year that it takes the market cap to then catch up. Like that's just, whoever is CEO of TSMC, that dude, like, we should get him on the podcast.
You totally should. You totally should get somebody from TSMC to just narrate how heroic. And they've got this technology lead for almost from 2018. Right. But even in 2018, it's taken 2 years for people to really say that, okay, this lead is there to stay and all of this before the market catches up and shows, reflects the same.
Right. Yeah. Cool. This was great, Mrinal. And then this is a good cliffhanger to, for a part 2. Record. And, a lot of questions are unanswered. For example, I would like to understand how the whole NVIDIA is playing out, right? So, how NVIDIA is going big there. What are the challenges that NVIDIA faces? And also some more details on, so just AI accelerators and so on. So just focusing more on that. So we should definitely...
Absolutely.
That will come in the next version of our interview.
Absolutely.
This was great. So any closing thoughts, or any trailer for the next part?
There is, I would say, like, the amount of action in the space is massively underrated and understated. It is like, cliffhanging, it is also like, extreme competition that even market leaders are facing. It is not that TSMC is sitting happy and fat and happy. It is not that NVIDIA is sitting fat and happy on where they are. Right. They are, competition. They're fighting battle by battle, day by day to reach where they are. And the challenges that they will have to fight and the battles that they will have to fight. So NVIDIA is, it's becoming a game of Go. Mm-hmm. So it's no longer you have one opponent. You have, NVIDIA's opponent is now, US. It is Google Cloud. And how does it, it is the standard AMD, which always was, but then also these new things opening up. And how does it continue, keeping, being the numero uno in this new landscape is a massively interesting problem.
And Mrinal, I think, like, when you'd spoken before, you'd mentioned this very interesting elephant versus whale story. So maybe you can tee that up as a teaser for what's going to come the next time.
Absolutely. Like, each one is a specialist. Like NVIDIA is a king in the GPU ring. AMD is a king in the CPU ring. And now we have AWS who's a king in the cloud ring. Everybody's trying to eat into the other market. Right. How do they do that is going to be fascinating. Yeah. Because each one is creating their chips. Is there a question like, do everybody start creating their own data centers? Does NVIDIA go that route? How does it keep what advantage does each one of have? What are their disadvantages? They're all champions in their own arena, but they're very weak outside it. And they're all trying to go into that. And the question is, will they or will they not? And, is it the story of an elephant in the elephant and the whale, where the whale is a king of the sea and elephant is a king of the land? But can the whale walk, or can the elephant, swim? That's the question.
Right.
Elephant versus whale, assuming that both are carnivores and both are desperate to become king of their realms. So a tiger versus a killer whale, or would I get the point, right?
Actually, it looks like more like Godzilla versus Kong, right? So
I love that. Absolutely.
Looks like that.
You didn't mention Intel though. Was that a strategic omission?
No, Intel's in the same. No, not at all. They are firing back. They have lot more cash in hand than other companies. So they are plowing it into anything that works. They have a portfolio of they have a CPU, they have a GPU, they have an out and out accelerator, they have FPGAs, they name it, they have everything. But they're not the king of anything. So the question is how will they come and really catch up here? And that's their challenge.
Amazing. So I think a good time to pause here before we go through the second part, right? Great. This was
Perfect.
Great, and I think let's dig deeper into each of these wars next time.
Yeah, thanks for coming on the show. It was awesome having you on.
It was a pleasure, absolute pleasure. It was a lot of fun talking.
Lovely. Talk soon.